is to really try to understand biological swimmers in their environment. There's lots of interesting phenomena, like, I showed at the very beginning this picture of the rhodobacter. This is not something I've particularly studied, but it's got this interesting kind of behavior. We have this coiled flagellum that's like a coiled rope in a plane. When the motor is not turning, when the motor turns, it turns into a helix. How does that work? E. coli is like the workhorse that's been studied by many, many people. We know quite a lot about that. There's a lot you can do to manipulate the genes. That's why people naturally look at that. Bacillus subtis is a little, less studied, but still we know a lot about that. But there are many interesting phenomena. To, echo Sid's point, I think this, we're all interested in deep fundamental organizing principles, but you will never be bored if you study phenomena, and it always leads to something, I think always leads to something interesting. I just have a couple more quick points. Maybe a little more detail. We got a lot out of the multipoles. You could do a lot about, you could make some simple calculations. It agrees with some experiments for the flow in the far field, but what about the flow in the near field for a microorganism? That's a real experimental challenge to measure. It's important for things that I didn't talk about at all, but things like, like eating. What is the role of flagella and cilia in stirring up the fluid to draw more nutrients nearby? We know that that's important. And, I've worked on this a little, but people like Ray Goldstein and Roman Stocker and Thomas Kaibo, they've worked on it much more. And they've gotten away with, looking at using what we've used in the far field, but there's a real challenge to understand the near field flow. And there's even a kind of counterpoint, like, which, Royce's lecture made me think of this. Food, but when you're in a location because of the long there's not just a question of eating, it's a question of not being eaten. So what is the role of that in evolution? These are all very big open questions. Let's see, the last point I'll make is, again, which I only just mentioned, but I think is a good area, is the question of the rheology of the fluid, what the swimmers are swimming in. So, some people think of me as a biological physicist, and I think that's fine. I think all of physics is kind of interesting, but my tendency is to look at some biological system and look for some interesting physical phenomenon and study that phenomenon, right? That's different than someone, which I think that's valid, but there's another approach, is just to study the organism itself and the physics that you need to understand it. So in the field of swimmers and mucus, or swimmers in something other than water, all the kinds of fluids that they commonly encounter, people have looked at one phenomenon at a time. It's too hard to study mucus all at once. So, mucus has a relaxation time. You could use the Oldroyd B model that Suzanne talked about. You can do experiments with artificial swimmers in such a material that maybe has more than one relaxation time, but you can separate out, make a fluid that is not shear thinning, so that you have these two different things that you separate. But now I think that, and people have done that, it's been very interesting, but now I think the time has come to really get serious and ask, what is the right combination of these effects together that's playing a role for swimmers? So that's why I mentioned this paper by Kamdar that came out in March, which I referenced in the notes, where they really look at all these different effects of, when you change the viscosity of a fluid, how fast does the bacterium swim? What is really going on in that real system? So there are many other questions about making artificial swimmers, but I think I'll just stop there.
So the lectures that I gave were, I think, quite different from at least the other ones that I heard here this week, because they weren't on a specific topic, right? That it wasn't swimmers or rheology, but basically I took the point that I was supposed to talk about experiment. And what I guess I wanted to emphasize is that you know, and I guess I felt very strongly after listening to Royce's beautiful lecture that, okay, the way he described some things, there was a place where he was getting his inspiration from. And then I thought about, well, your lecture and Suzanne's lecture and San's lecture, and everyone seemed to be getting their inspiration from a slightly different source. And certainly, being a theorist, I guess you get a lot of inspiration from the mathematics, and you start from mathematics and you kind of see where it goes or what does it imply. And I mean, that's certainly one way of getting the inspiration. So that's starting from that point of view. There's another point of view of where you can get the inspiration from is, well, there's data. And so you come and get the data. And so you might think that that's what the experimental stuff is about. And that's not what I was particularly talking about, because I do think, yes, the data is a place for inspiration. You see this data, and how do you explain it, and so forth. And that's one aspect of it. And so that's certainly another place that all of us can get inspiration from, is you see data that comes across your desk and you say, well, how do you explain that? But the kind of inspiration that I was trying to emphasize, I think, was there's inspiration by just looking at the phenomena. It's the physicality of the phenomena which somehow grabs you and then makes you want to understand it. Whatever the data is, there's something that went on at almost a qualitative level before you got into this quantitative looking into data. It's not that you, I mean, I don't want you to think, oh, he just takes pretty pictures and then he leaves. I mean, we do care about what the data is. I mean, and that's a very serious part of it, but that's not necessarily where the inspiration comes from. And so that's what I'm trying to emphasize, this distinction a little bit, that it's a little bit of a different flavor, I think, from what other people have said here. And so then what are some of the other things? So that was kind of where I came from in trying to prepare these lectures, was try to emphasize some of those aspects. But in doing this, then putting it together, what I also then began to want to emphasize was not just where the inspiration came from, but then you look at these phenomena, and that, as the title of this summer school is, across scales. And that was something that the experiments that I tried to show had implications across scales. And so, the most obvious one, drop snap off, I mean, that occurs from, nuclear scales to the celestial scales. And it's just very nice to be able to study it in the lab. I mean, and so this was kind of one case in point, but I think I tried to emphasize that through different experiments. That is, the granular stuff hitting a target, that looked like the quark-gluon plasma to some extent. And so these were some of the connections that I tried to draw. And then the other part was, I tried to bring into this, was that I was given the title complex fluids. And as I said at the beginning, I wasn't quite sure what I had to say about complex fluids, but that if you just take that as a much more general thing and ask, okay, so where do you find the fluids? And that's where I also wanted to emphasize that, so we started with, ordinary fluids, the drops breaking up, splashing, whatever. But then you go and you say, okay, how about just granular material? That didn't start out as a fluid, but if you manipulate it in the right way, oh, now it's a fluid and we get to say something about it as a fluid. You ask about the electrons in in graphene, and you ask, okay, so is that a fluid, or is that something that I'm only supposed to look at if I'm doing hard condensed matter? And you say, oh no, you can actually think of that as a fluid, and you can then find new phenomena that come out. And so that was another part that I tried to emphasize, is somehow that these things There are lots of ways of making these fluids that it's a very kind of broad set of topics that they transcend scales. And then I guess the last thing I just wanted to keep pushing is that, you're told that nature's supposed to work in one way. And yep, I've been told I'm a good boy. Yep, I will try to find nature working that way. But time and time again, when you do the experiment, you find, oops, it doesn't work that way. And that there's a lot to be learned by doing this, but you have to do it with an open mind. Because if you think that this is what you're supposed to find, I can assure you, you will find it. I mean, you can always find a way of ignoring the things that don't look so good and only taking the things that do look good. And, this happens over and over again in so many of the studies that we've been involved in. And so we kind of see that. And so that's another aspect of this, is that, nature is talking to you, but you have to listen carefully. And I guess that's the mantra that I like to have: listen carefully.
Could I ask you to just say a few words reminding us about what Suzanne talked about? She couldn't be here, but I think you're the best person.
Sure, I can try to do that. I think she gave a very she had this theme of shear banding throughout her lectures. And, what I really enjoyed about that is her work where she applied it to active matter and used this picture of shear banding to explain why you would get a spontaneous flow. So I think that's it's a slightly different viewpoint, very physical viewpoint that's not seen in a lot of the other approaches to understanding that. So this S-shaped thing, I'm in a solid mechanics group at Brown, and she mentioned this. You see this all the time in the field of solid mechanics, but things are a little different in these particular systems that she's been studying, these polymeric liquids. I don't know, I'm going to actually spend a little more. I haven't read all of her papers, but I'll just spend some more time doing it. I think it was a nice overview.
So Son had to leave early to deal with a canceled flight. So I just thought I'd say a few words about what he talked about, which was a kind of mainly a classical Hamiltonian approach to the quantum Hall effect, and which had a lot of elements of hydrodynamics in it, and talked about conservation laws and area preserving diffeomorphisms. It was mainly focused on the incompressible states, the states of matter that have a gap to excitations. But I just wanted to put this in a larger context of his work. So he's done some really nice work recently on the nu equals 1/2 fractional quantum Hall state, which is a compressible state, and also on bosonization of fermions and Fermi liquids in higher dimensions, again, using some hydrodynamic ideas. So he's been really creative at kind of pushing the hydrodynamic pictures in these different quantum systems. So I thought that was a kind of a nice way to end in this fourth week of the school, just showing the range of applicability of hydrodynamic thinking. So not only have we had talks that have ranged over classical and quantum systems, then as Royce pointed out just a little while ago, we had this tremendous range of physical scales that went from the quark-gluon plasma, so at a scale of 1 Fermi or 10 to the minus 15 meters, to the galactic scale of like 100,000 light years, which is, if I did my calculation right, that's about 10 to the 21 meters. So that means that the school spanned 36 orders of magnitude, which is, I think, pretty impressive. Peter or Leo, do you have anything you would like to say? No, I haven't done that. Yeah.
So let me just sort of somewhat different topic, right? Both Brad and I are involved deeply with the APS, American Physical Society. And maybe 10 odd years ago, they actually created a climate physics topical group. And I thought I'd just give a shout out to that. If you're a member of the APS or would like to become a member of the APS, please seek out, it's called GPC. Please seek that out and join. It has about 500 to 600 current members, and we'd love to grow that. We're very, very active on the intersection between physics. So there's people coming from very, very fundamental physics backgrounds like Brad and myself, as well as people who work actively in the climate area, as well as people who do more laboratory-based fluid dynamics stuff. So they're very active on the intersection between physics and the geosciences. And really, historically, it's remarkable to me how small this kind of representation is within APS and why it took until whatever 10 years ago for people to get around to actually encouraging that kind of research and representation within APS. So yeah, that's the end of my shout out. So please join. The more young people, the better. And again, the March meeting is our main set of events for that. And that's a huge meeting, and it's fun to come to, even if it's not just for climate stuff.
Yeah, maybe I'll just follow on. Yeah, so I just wanted to follow up on something you said about looking at swimmers in more complex fluids. So I guess in part it's like a question of thinking about like liquid crystal-like fluids. So not necessarily complex rheologically, but complex in that they're, break some spatial symmetry, rotational and translational symmetry. So, that for me kind of would be a natural thing to explore. So one question is, has that been explored, or what is the status of that direction?
Sure. Yeah, that's a good question. Actually, I've been interested in that question for a long time. And so I don't know, 10 or maybe more years ago, I started looking at just simple models of swimmers in a pneumatic liquid crystal. I thought there'd be a lot of interesting things to happen, but I was a little bit afraid to give this problem to a student because I didn't think anyone would do experiments on it. I didn't know of any experiments. But then I was talking to a student, this person, Ski Krieger, and he did it anyhow. And so we looked at it at a very sort of simple level. And then, of course, now there are experiments here. Norris is doing some really interesting stuff. And there's been this work by Igor Aronson's group, the swimming in living liquid crystals. And there are a lot of interesting questions where you can't do the things that so here's one thing to say. So, Eric Loga has often said this to me, and vice versa, like, resistive force theory shouldn't work very well, but people apply it all the time and it works better than you expect, like in the sense that people have applied it to viscoelastic systems where you have nonlinearity. It should just be a dead stop, shouldn't work at all. By the way, is it recorded?
Yes.
Okay. So maybe I should be more precise about citations and things like that. So one question is, how far can you get in pneumatic liquid crystals by maybe trying to use some nonlinear or using some linear ideas, even though we know there's going to be nonlinearity because if the liquid crystal wants to align with the helix, you can't just add things up. But the first step, I think, would be to see how these ideas fail. And then there's the other side of it, which is you could think of this one as an interesting physics problem. There's new phenomena that Nora sees when she looks at these swimmers in a pneumatic liquid crystal. Two, you could think of it as you're using the pneumatic liquid crystal to probe something about the swimmers, something about their behavior, something about the way that their bundles form. She's looking at Bacillus subtilis. And then again, getting back to something I said earlier, which I think is not, people are only sort of just starting to do this, is looking at swimmers in things like a biofilm or mucus, where you would have some anisotropy, but it's not just a liquid crystal. There's something else going on, but maybe the liquid crystalline aspects, are very important or maybe even dominant. And so I think that's a big area that is going to be very interesting in the near future.
Royce, you've attended all the talks or almost all the talks.
No, I'm
Royce?
afraid I'm not that diligent as the students.
Okay, well, do you have any final thoughts?
Well, I think I said it all already the last hour. I put in as much as I could in the last hour, so I leave it up to you guys. May I?
So maybe I'll bring up another point in the form of a question to Royce. So, in systems like swimmers or self-propelled, constituents, that's a non-equilibrium system, but it seems like quite different than non-equilibrium systems where you have an external force and you're driving some interface or some contact line through, some maybe disordered medium. So I was wondering if you would comment on that, some from a more general non-equilibrium StatMech perspective.
Well, I sort of fall back on the how you implement the equations of evolution, right? So you write down your variables that you want to consider, and then you somehow decide how these variables change. And as far as the variables are concerned, they may or may not know what is the origin of the force. What is certainly true is that the drives could be boundary drives rather than internal and everywhere. And so that can make quite a bit of difference because the ones that are in the boundary may or may not have an effect on the internal system. So in fact, while I'm listening to the talks about turbulence cascade, and I keep seeing pictures of the energy being plotted against, I'm sorry, the distribution of energy, and there's an inertial range, and the energy is supposed to cascade from one frequency to another. Oh, I think I've lost you. Is that right? Hello? 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 I can't hear you.
The internet cut out for a bit, so we're going to come back to you in just a moment.
Okay.
Peter, I promised last week that you would say something about your career trajectory.
I'm not sure I want to. I started out life as a condensed matter theorist at Cornell University. So I did my PhD under a fairly famous phase transition person, Michael Fisher. And I progressed. I was one of the few people in his group who actually did some quantum mechanics. We were doing superfluid helium stuff. So that was actually relatively rare in his group. And so that allowed me to make contact. I mean, again, at that time, Cornell was sort of the gorilla in the world for low temperature physics and helium physics. And that field is more or less almost gone away now, unfortunately. It's very sad. But I moved into sort of quantum phase transition stuff, superfluids and disordered media, things like that. And then at some point in the 90s, I branched into fluid dynamics because I saw that there were a number of sort of scale invariant problems, you could, I guess, in some sense, and statistical mechanical problems that in terms of which you could phrase fluid dynamics problems, including homogeneous turbulence, things like that. And also I did some work on understanding sort of stability of Jupiter's red spot and things like that. So, I very, very idealized models. So that's my, that's what I love, really idealized models that have beautiful physics in them. And then for various reasons, I ended up moving away from academia, and I'm working for now what, basically was a defense contractor doing sort of DARPA projects, Air Force projects, huge array of things that occasionally intersect climate and things like that. So we've worked on problems related to very, very long range acoustic propagation underwater, things like that. Not directly related to climate, but that does intersect that area. A lot of ionospheric physics, because it happens, you can bounce radar beams off the ionosphere and do very long range detection, things like that. But understanding the ionosphere, again, sort of brings you back into geophysics, geosciences, geofluid dynamics. More of my day job doesn't have much to do with that. More like, again, more conventional radar problems, things like that, and also benchtop optical problems. There's a lot of quantum sensors that are coming into being now that could easily surpass any classical sensors. We have some projects now, Rydberg Atoms, right, where you sort of knock an electron into a very high orbit around an atom, and it has a very, very high dipole moment. And principally, you can build really, really good antennas out of those. Of course, it's extremely difficult because those electrons don't stay there very often. You're constantly eliminating anyway. And there are tons and tons of different, very high level hydrogen, high energy states and so on. So I think that gives you a sort of picture of the sorts of things I've done. I keep sort of coming back to fluid dynamics and geophysics, things like that on an occasional basis. I've probably learned more here. As you can tell from the questions I was asking, I probably learned as much or more sitting and listening to these lectures. It's a rare opportunity for me to hear what is going on such a broad array of topics. So happy to entertain any further questions.
Well, I mean, so you asked a specific question about career, which, since I think we're obliged to try and answer it, even though our wisdom is very meager on the subject. And so, it depends on what you want to do in life, right? I mean, that's part of it. Now, one of the things that has always been said for physics is that getting a physics degree is not so much because you've learned one specific set of things, but that you've learned something about how to think about things in a new and creative way. And so if the question is, well, what industry would be interested in me if that's the case? Well, many industries are just because of that, of the training that you've had, to deal with lots of data, for example. So who would have thought that a particle experimentalist, one of the thousands of people working at Atlas, well, what are they good for? Well, they're good for lots of stuff because they know how to deal with enormous sets of data and new ways of thinking about it. How do you look at it from one side, another side, another? I mean, so all of that training is there. The training in the lab of how do you go about making something work? How do you make electronics work to do something? And even if it isn't that you know it, it's that you know how to know it. I mean, so that's part of what the issue is. So I caught one thing about what you said, which was a little bit, a worry, is you said, well, aside from having fun, and you used that word fun as if that was a derogatory thing. And I hope it's not. I mean, that's the thing, is that I hope that the fun part is still there, irrespective of what area that you work in. And why is it there? Because you just love playing with ideas, or you love playing with whatever aspect, if you love manipulating equations, or you love thinking about what these might imply, or love in the lab. I mean, these are the things that turn you on, and you're getting a training in doing that by learning these things. And so, if the idea is that you want to stay in academia, well, that's another thing, but then you don't have to worry about being useful since academics aren't very useful. Yes.
Can I chime in on something?
Please. Go ahead.
I really appreciate what Sid has said with many, many things, especially this kind of a outlook of life about nature and what have you. But as far as the last bit that he was mentioning about, if you guys are worried about careers and so on, let me tell you what I do when I was the department chair. So a lot of the times I have to deal with parents coming in with their kids from high school, say, and the kid wants to do physics and the parents want them to do something else, engineering or whatever. And because they have really no idea what physics is. And so one thing I discovered that really made a lot of impact on these parents is to say that think of the training of physics as training to be a stem cell, at the end of which you can become whatever you want, as opposed to, say, training to be a civil engineer, at the end of which you are more or less a civil engineer unless you are retraining yourself. So that really made a lot of sense to the parents. And so think of yourself as a stem cell, that you're ready to take on whatever challenge there is and develop into the cell that is needed. Incidentally, in case you don't know what a stem cell is, when babies are born, there's only one cell. And then eventually there are lots of cells, but before these cells change into different kinds of cells, whether it be hair cells or bone cells or brain cells or liver cells, they were all stem cells, and stem cells can develop into everything that the body needs. So that's the analogy. And that's what I hope you would bring with you when you think about, training to be, to get a PhD in physics, is that you will be a stem cell. Does that help?
Let me maybe try to chime in on the topic. So on this question. So, the answer very much depends on whether, and I think Sid, like what Sid already went along that direction, very much depends on whether you're asking to be successful in, outside of academia or inside academia. So outside of academia, as Roy said, you guys are all trained as stem cells, and you'll definitely not have any problems. Already having reached this level, you're all extremely well trained for, any technical career. And there's definitely none of you will have an issue. It's much more subtle and much more challenging, unfortunately, to stay in academia and to really make it, to the level of, assistant professor, tenured professor. And, it's easy for us, seasoned tenured professors to advise you to have fun and to not worry about any strategies of trying to make it in academia. But, reality is it's very challenging, and some of it is out of your hands. There's definitely luck involved and luck of picking a problem. And so what I would say is I recall a really beautiful lecture at the March meeting a few years back by Tony Leggett, where he was emphasizing that, in this publish or perish kind of an environment, he was emphasizing that you should always everybody should dedicate some fraction of their time trying to answer questions and trying to work on problems they have no idea what the answer is, just really explorative and just completely sort of, just having fun and just trying to answer questions that you a priori have no idea what the answer is. So that's one comment I'll make. And so, even so you can have a hybrid approach where you're on one hand focused on trying to, produce and try to make it, but at the same time you have to balance that, and the balance is different for different people, to try to have fun with problems that are not strategic, but are just, you really are purely curiosity driven. So that's one thing I will say. The other thing I will say is that's maybe helpful is, when you're in the trenches there working on your PhD or postdoc and trying to get a job and trying to produce results, and you're struggling and you're having a hard time, you have to remember that it's not just you. It's the subject is difficult, and getting a job in that subject in academia is extremely difficult. And so, you're not alone in that struggle. Personally, I had a pretty unsuccessful postdoc at the University of Chicago, and first year I didn't publish anything, and I remember driving on Lakeshore from from Evanston to Hyde Park every morning, thinking after 1 year that I've done nothing, basically, just read papers and try to do calculations that were all dead end. I remember thinking every morning, like, is it today that I quit physics, academic route to physics, and, go find a regular job? And, I stuck with it, but it could have, coin could have flipped differently. So as you guys go through and struggle to find a job and struggle in your path to academic physics, just remember that, it is difficult. It's not just you. So, and stick with it.
I'll just make a really concrete suggestion. If Baylor were here, he would point out that there is a much higher ratio of jobs to applicants in climate science than there is in physics. It's really kind of amazing. There's this huge labs here in Boulder that are higher, but beyond that, Stanford just got more than $1 billion to start a new climate science school. And I'm on a panel, APS committee that's looking into direct air capture of carbon dioxide. And that field is exploding right now. There's something like 60 startups funded by venture capital. They're trying to hire physicists. And so if you broaden your view from what a physicist is a physicist somebody in a physics department, to the kinds of work and the kinds of thinking that physicists do, then there are, I think, many opportunities. And unfortunately, climate science is going to be a big opportunity because of the rate at which things are changing. So maybe some of you will move in that direction.
Can I chime in, Brad?
Yeah, please.
I don't remember who wrote this review article about climate science, but I remember very distinctly that it says, the planet says to you, we need you, physicists. So think about that. The planet says, we need you.
Right, that was in Nature.
That was in Nature. Who was the person who wrote that?
I don't remember. It might have been just an editor.
Well, anyway, I had it in one of my talks, and if I could find it out, I'll share with you guys. But to go back to the statement, well, all of this theme the last few minutes is that another thing that I try to remind people who are studying physics and wondering what they would do and so on is the following. If you look at a typical academic department, not in physics, you would find physicists in there. So essentially all the engineering departments have physicists in there. And now biology departments are full of physicists, chemistry departments are full of physicists, but essentially none the other way around. There are very few, biologists, PhDs in physics departments and so on. And it keeps going. And there was a time when I was able to say to the to the potential student and parent, if you want, you can be the Chancellor of West Germany or Germany at that time. So physicists have careers at all different places, and that is what I meant by being a stem cell. So the opportunities are wide open for physicists.
Okay, why don't we move on to a different question? Oh, yeah.
Hi. So this is specifically about active matter. So in the school, we had a lot of lectures about how interesting it is to study. And in terms of colloidal active particles, like it's usually about the basic science that we study. But I want to know, like, what are the applications of it? Of course, we have seen that, okay, there's microbots or drug delivery that is possible. But in terms of active particles in complex fluid, is there any specific application that is possible? Like, because it's always good to have some kind of an aim when you're doing some kind of studies.
Tom?
Yeah, I guess as someone who sits in an engineering department, I should have a very snappy answer to that. But I don't. You know, in an academic and even in an academic engineering department, you know, we still work sort of basic engineering science questions. You know, this sort of connects to the previous question. There are very hard constraints, right? We have to get funding, especially in engineering. You're expected to, you know, bring in funding, and so there has to be some idea of an application. I think there's still a lot of room to study the fundamental physics without actually saying that you're going to deliver some device. I think in this area, we're just not there yet. There are many different ideas, and it's not really clear which ones are going to pan out, right? How do you steer something in a Newtonian liquid? We can't really do that at the micron scale. So, you know, it's often when I joined an engineering department, you know, what's the difference between a science department and engineering? The attitude at my place at Brown is that, well, the scientists are working on things that'll be, there are applications that'll come much later than what the engineers are working on, but it's the engineers in academia are still looking pretty far out. So that's not a very satisfying answer, but my own opinion is that I think it's still at the point where we should be just trying everything that looks interesting, and it's not clear to me, you know, which directions are going to lead to real, you know, devices.
But, you know, I'll answer a question with a question. I mean, why isn't, for example, drug delivery to some region of the body where, you know, you have to go through mucus, the drug has to be delivered through mucus, is an example of sort of active matter potentially going through some non-trivial fluid, swimming in some non-trivial fluid. So it seems like even that is a immediate direct application. I mean, there may be other things that are less obvious, but it's hard to anticipate.
Do you want to?
Just a quick follow-up question on the career discussion that was going on before. So I don't think there is a point where someone, at least for most of us, the point when we would start applying for faculty positions, for instance, is very much dependent on your individual, I guess, progress with publishing, etc. But I wanted to ask if you have any kind of advice for what kind of criteria we might look to decide to start applying for faculty positions as opposed to maybe another postdoc.
So I'll answer this in terms of what the criterion are for getting tenure at my institution and in my particular department, because that's really what drives our decisions when we interview people. We want to support people. We want them to be successful when we hire them. So it's a very simple criterion. They have to do significant independent work. So there should be some sign of that in the application. And there are many different ways to show that. I think we've gotten a little better at this by not just looking at numbers and things like that. Of course, if someone solves a great problem, it's very easy to tell that person is likely to be successful. But here's an example, doing something significant, maybe in a slightly different field where it's clear, different from your PhD thesis, where you've written a few papers, so that there's a clear, sign of significant work. The other thing I'll mention, this kind of connects to the previous question, some good advice that was given me when I was a graduate student is that looking for a job is not some condition that flares up, at the end of your graduate career. It's a chronic condition. And that goes all the way through being a postdoc. It goes all the way through being an assistant professor, because, every talk, I think I met Brad actually at Aspen, and that somehow led to a seminar in the physics department. And when I was a postdoc, and it turned out that, Rob Phillips, someone in engineering, was in that seminar. So when I applied, he knew who I was. So, even if it's not natural, just, making connections, being as visible as you can, I think is also very important if you are on the road to becoming a faculty member. But I think we'll still work together, right? Based on this month of lectures and things.
Thank you. So, okay, this question is different from previous questions. So I'm curious about when we're doing the research, like based on your experience, how do you get the inspirations or motivations? We see these beautiful experiments of droplets or splash or micro swimmers and many other things. So how did you get the ideas or motivation to study these systems? Did you look at the droplet or reading papers? I don't know. Yeah. So just
well, it's a little bit of all of the above. I mean, you just hope that you're going to be lucky to be bombarded with things to some extent. I mean, that's why you keep going to talks. Most talks I don't get a thing out of, but every once in a while there's a great thing, and so that was worth all of those other talks to have sat through to have gotten that one idea. So it's not like you can just say, okay, here it is, and this is how you get it. But I mean, I think that there were, in my own experience, there were a variety of ways. I mean, so I had a colleague, Leo Kadanoff, who was interested in singularities. And he kept talking about singularities running around the unit circle, and Julia said in the complex plane. And finally, I just couldn't stand it any longer and said, "What the fuck? What is this about? I mean, please tell me, what's it useful for?" And because I diligently went to these talks and tried to figure out what it was about. And so, well, maybe it could have something to do with drop snap off. So, okay. So then once there's a bit of reality, then you can begin to explore that and see what it is. I mean, I had no idea, we'd never done anything like that before, but you can start playing with that. And so it's just playing because it was fun. I mean, I still do like the idea of fun in this, and it should be enjoyable. Otherwise, what are we here for? So that's one thing. But then there were other things which came from a completely different thing. So one thing that maybe Chloe talked to some of you about is this problem of coffee stains. So where did that come from? I mean, that didn't come from anyone at all. I mean, that came from just waking up one day and looking at my kitchen counter, and it was a mess. And so, what? And then you say, that's not the way it should be. And why was I receptive to that particular idea? Was Well, way back before I even started graduate school, I had a summer working at Woods Hole looking at bioluminescent organisms, and it was brighter in the center and darker around the edge. And where did which way, I forget which way it was, but it was something like that. And so where did that come from? And so I was primed to think about, oh, well, why was something around an edge rather than in the center? And so, but that was, you know, is so I mean, my philosophy of all of this stuff is that we're bees. And what we do is, and do reasonably well sometimes, is we go and look for flowers in all sorts of fields. And you pick up pollen one place and bring back to another place. And you suddenly, something new got created because you took an idea from here and an idea from there, and they came together. And so, well, if you only look in the region right around where that one flower is, you're not going to get a very different pool of genetic stuff to be putting in here. So what's good is, oh, if you have some thoughts from, you know, where you plop down in lots of different fields over your career, and then you're able to pull out an idea from there and combine it with an idea here, and lo and behold, something, I mean, it could be a beautiful flower come out, or it could be a thorn, I don't know, but it's something different that hadn't been seen before. And so that's kind of what this is. So both of those examples were things where, okay, there was something, you know, something spurred an idea. A flag went up that said, oh, this is not right, or this is different, or this is, and pay attention to that. And so, you know, and no, I keep saying, listen very carefully to nature. And so I can say that about the experimental lab, but I think everyone in doing whatever aspect of theory or whatever, you say, oh, this doesn't look quite right, or something here, why is this, you know, so you start trying to listen very carefully to what those little question marks come up in your brain as you're doing this. And I think that's where you get the inspiration to go on and to try something different.
For me, you know, doing physics is, I always strive to develop intuition. So things are like, even in the most complex phenomena, I'm not happy until, even if it's subquantum, subtle quantum phenomena, I'm not happy until, and I don't feel like I understand it until it's kind of a ball spring kind of a thing. This pushes on that, and that makes it want to go this way. And, you know, to develop that intuition, I find it very useful to be exposed to, as Sid was mentioning, to as many ideas from as many different areas as possible, because then even the same phenomena is really nice. You know, it really drives me, and I really love being able to understand a phenomena from like 3 or 4 different perspectives, because then it teaches me about all that, those other areas, as well as helps me understand the phenomena. And, you know, so for that, you want to not just go to seminars in your area of study, but embrace colloquia in areas that you're not, you know, working in. Read papers as much as you can in fields outside of your area. When I was a grad student, we had, you know, like a stand and Jefferson lab, Jefferson building library. There was a stand where all the journals were put out every week, the new journals, and there was no archive at that time. And God, I'm pretty old, but you know, so I dedicated every Monday, I would start from beginning of that long rack and read, you know, most, you know, sort of main journals, all the PhysRev journals, and like literally go through them. Of course, I didn't read the paper. There's no way I could read the papers, but I found it extremely valuable to just read the introduction, because then all of a sudden I'm reading about some field and I'm reading the introduction. And the introduction, you know, for the most part, not all papers are successful, that you can kind of get a germ of what the field is about or what problems are about. And when you first start out doing that, almost everything is unfamiliar. So everything is, you know, very challenging. But the more you do that, you start realizing it's actually finite. you start seeing the same problem being discussed in many different papers. So then it becomes easier and easier. So now, we don't go to libraries and read journals anymore. I don't. But then I replaced that by reading the archive. I don't go to sleep every day. I do not go to sleep until I go through all the condensed matter archive papers, the 100 papers, which means, what does that mean? I mean, I only read the abstracts, and out of 100 postings, I might look at only 5 or something like that. But I look at every abstract. And so, and again, when you first start out, every abstract is irrelevant. Like you have no idea what the words are, why are they studying this? You have no idea. But the more you do this, and if you do it diligently day after day, your scope just runs incredibly, and it becomes, you kind of embrace the breadth of it. And then when you work on your problems, it's amazing how some little sentence in some obscure paper, not in your field, a bell goes off and you're like, oh, wow, that's like that. And, and it helps you in your research. So it's both broadening, becoming a better stem cell, but it's also helpful to you in your research.
Any other questions? You want to go back to Royce?
Yeah, so maybe if Royce could comment on.
Yeah.
If you could comment on my question that I brought up, sort of, do you view the two classes of non-equilibrium systems,
the one that,
belt and the other
Yeah.
with driven externally,
yeah.
somehow two different classes, or is there qualitative difference?
Good, yeah. We got cut off by the internet problem, right? Right, so what I started to say is that if you look at the individual configuration, the variables associated with the configurations, then assuming there is not long range interactions of some kind, they feel, let me call it force, okay, in the sense that they're trying to go from A to B somehow. And now the question is, where does that something come from that was associated with the two classes you mean? That something could be internally generated, like the active matter, like the flagella and so on, or it could be being pushed by things around them, like in the case of fluids, you would have, say, shear, and then the drive is actually at the boundary. So that's what I had tried to allude to when I talked about the different kinds of drives, and obviously the ones that are imposed at the boundary are inhomogeneous, and they depend on quite a bit more complicated things, because you have to talk about how the system itself responds to each other and correlations and things like that, as opposed to just generated locally and then you ask how they behave. So what I'm aware of, and it doesn't quite answer your question exactly, what I'm aware of that seems to be quite crucial is that these probability current loops, some of them are local loops, and some of them are big loops, and some of them are global loops. And so by global loops, the easiest example is this one that I mentioned during the lecture. If you have a biased random walk on a ring, then it's a global current and will never go away, no matter how you coarse grain. I mean, you can coarse grain down to 3 sites and it would still be there. 3 sectors, it would still be there. On the other hand, you can have non-equilibrium drives, which are very local, and you get local loops like this. And then if you coarse grain, they are gone. So one of the things that we learn about non-equilibrium, the sort of non-equilibrium physics that we do, is that that seems to have a fairly major implications, because one, you can coarse grain away to the point that you can describe the system by equilibrium statistical mechanics. So all the currents can be gone by looking at it the right way or coarse graining it the right way. And then there are situations where it won't go away. So turbulence, for example, will never go away because they are imposed at the boundaries, right? By definition, it's something that where if you coarse grain to the point that the input and the output is at the same place, you have no system left. But if you coarse grain to a point that you have an input, you have output there, and at least one thing in between, then at least you would have three things to talk about, right? So that's what I mean by, that's one of the things we've sort of learned is to watch out for these currents. Are they global or are they local? Maybe this is a good time to, talk about currents in the context of these Komagov loops. Shall I do that, Brad?
Yeah,
Hello?
do you have a slide or two you want to show?
Yeah. I mean,
Okay.
this is sort of in the spirit of answering the question of the student that was asking about Komagov loops. So let me go to this slide. So I'm back at this master equation. We're talking about these rates, and the question is what obeys detail balance or what doesn't obey detail balance. So I've changed notation on you. They are not called R's, but W's. And instead of R from C to C prime, it's just IJ. Okay, so this is the notation this is the rate to go from configuration J to configuration I. So here's the ratio of the rate of J to I versus the backward rate. Okay, and so the original detail balance is presented as something that requires you to know what the stationary distribution is. But that isn't the point. And the Komagov criterion is the following. Consider a closed loop, like I to J, K, and N, and so on. So it's a loop like this, that goes like this. And now you just take the product of these rates all the way around the loop, I to J, J to K, and N to I, all the way around. And then you consider the product in reverse, going the other way, I to N, and so K to J and J to I, going around the other way. The question is, are the product of these rates the same for all loops? Okay, and so the Komagov criterion is whether it's the same or not. If it is the same, then you say the system satisfies detail balance. And it has to do with time reversal and things like that. But in any case, these loops can be, some of the loops can be local and some of the loops can be global. And I can now stop sharing and going back to waving my hands. So for example, you can have take a look at a two-dimensional lattice, a person doing random walk on 2 dimensions, okay? So if you just imagine the person going around like this and like this and like this and like this, and if it's biased to go down, say pretend that you have gravity, okay, then clearly, well, it's not so clear, but you can work it out that if you go around like this on a gravitational field, then the rates for going around the other way would be the same. So the Komagov condition is satisfied locally, but it is not satisfied globally if you allow periodic boundary conditions. In fact, when I was giving these talks at the very beginning, we used to say that, well, as far as the driven system is concerned, it looks just like gravity, except that you somehow piece together the ground with the top. And that's the global connectivity, which is very, very different. And it makes me think of, the topological issues that Brad keeps bringing up. And one of them gives you a global current that will never go away. And there are local currents. You can imagine there are local currents, but they would go away if you just look at it in a local fashion. So those are the things that we have learned a little bit to watch out for, and for what that is worth. Does that answer your question, Leo?
Yes, it does. I just have a quick follow-up. Is the Kolmogorov's formulation that you just stated, or criterion, is that the same as the traditional definition of the, it's equivalent to the traditional definition of detailed balance that you had in the first line?
Well, the so-called traditional, so the one that I learned when I was a student, that the incoming and outgoing rates have to be the ratio of the Boltzmann
Correct,
factor.
yeah.
So that one requires you to know ahead of time what is the steady state distribution first. And that's hard, of course, because you have to solve the problem first.
I see.
And so that's the reason for not using it. What happened to my share screen? Here, let me start sharing again. Oops, there it is. Let me just go back to this thing. I don't think I need to go back up. Come on, do something.
Yeah, you had it on the previous slide.
Oh, here it is, right?
Yes.
This is the traditional way. This is e to the minus beta h, so it's the difference of the two Hamiltonians, two Boltzmann factors. So this is the way that it's presented to me when I was a student. And what happens is that a lot of the people who try to do simulations or equilibrium systems, like the Ising model, they were basically drummed into their heads that if they choose they can choose one way, whatever they want, but if they choose the other way, whatever they want, but not obey this, then the system is not going to go into equilibrium. That's what they're told, and that's what they always make sure that the ratio of the return rates is this ratio. But you see, it requires you to know the solution of the problem first. So if you know where you want to go, then you know how to make the rates to get there. But if you don't know, so if I write down a set of rates for the stock market, or for how the infections are transmitted from A to B and so on and so forth, if I write down a set of rates, how do you know it obeys detailed balance or not? Because you don't know what the P stars are. And the test is to go and make sure that every loop obeys the condition that going forwards, this product of the W is one way, is the product of the W is the other way, okay, for all loops. And now this sounds awful, but in many of the things that you can write down, typically you don't have to do very much. You can just look at very simple loops and show that it's not equal. It's easy to show that it's not equal. And then you say, okay, I'm dealing with a non-equilibrium situation and I cannot expect simple answers. And that's the end of the story. But if you do know this, then, by the way, this condition is equivalent to mathematics where you call integrability. So think of these rates. Think of these rates as specifying a vector field. The ratio of ij to ji, think of that thing as e to the, is kind of a vector field, right? Think of it as e to the difference, and that makes it into a vector field. That's what I meant by it's a little bit gauge-like and so on. So if this ratio, which can be written as e to the something, let me call it aij, it's like a gauge field, then what this condition is to say that you can take that vector field and go around anywhere you want and you'll come back to yourself. So that's the equivalent. This condition is the equivalent of the curl-free condition of the rates. And
but this seems
curl-free condition is what allows you to integrate and get an answer right away. Yes.
But this seems a little strange in that, you're tying a time reversal symmetry, but
Yeah.
if I have some system with friction where time reversal is broken, or I have a magnetic field, can I, that system can still equilibrate. There's nothing about non-equilibrium about that system a priori. It could also be non-equilibrium, but I'm confused a little bit by tying detailed balance to time reversal and equilibration.
Good. That's very good. when you mention So there are two issues here, which are separate. One is about friction, and that's dissipation, right?
Right.
So that's why I tried to weave in fluctuation dissipation. So if you have dissipation and no fluctuations, then it doesn't obey time reversal, and you just go down to the lower state, and that's it, right?
Mhm.
So when you get there, you are in equilibrium. So how should I say? If you're pure dissipation, it's non-equilibrium in the sense that the evolution doesn't obey detailed balance, but you know how to get to the stationary state very easily because you have pure dissipation. I mean, these are just words, okay? But the way that it shows up in these conditions is, imagine that one of these is 0 and the other one is non-zero. So you can just go one way and not the other way. That's that tacit business, right? So those ratios, they're never going to be the same. So if you put a wall somewhere, all the particles are going to jam against the wall, and that's the end of the story. And those are what we call absorbing states. So once you get there, you never come out. So if you only have a system with friction and no fluctuations, then you would just go into what we call absorbing states. Okay. And in the case of population dynamics, it means that the species have gone extinct. So there's no more life, and that's the end of the story. Now, magnetic fields is a very different story, because when we talk about time reversal, I have not tried to be complete, in the sense that if you apply time reversal, you remember you have to reverse all the velocity, the so-called time odd variables like velocities. So if you don't reverse those, then of course it doesn't, ordinary F equals ma doesn't work, right? If you look at Hamiltonian dynamics in the phase space X and P, it goes around in loops. Right? So you can say, well, look, there are current loops in ordinary simple harmonic oscillator. It just goes around loops. And there, time reversal is associated with even flipping and in flipping the momenta at the same time. So magnetic fields belong to that category. And there's another level of subtlety as far as time reversal with those variables are concerned. I've tried to stay away from those types of variables for that reason, just to make it less complicated. Does that help?
Royce, well, there are Hamiltonian systems that break time reversal symmetry spontaneously in their ground state. So how would those ground states, so they might be twofold degenerate, for instance, with those, how would those fit in?
Right, you mean like a superconducting ring, right? For example.
Well,
So I'm not, I'm not, so I'm trying, so this is one of the things which I haven't really become completely clear in my mind, how to separate out a superconducting ring from non-equilibrium steady state, right? Because a superconducting ring would just do that forever.
Right.
And it is not connected to two reservoirs.
Right.
Right.
Well, a ferromagnet could be coupled to reservoirs, and under, below the Curie temperature, it effectively breaks time reversal symmetry spontaneously.
Okay, I'm not familiar enough with those systems to answer your question.
Let's chat about it privately.
Yeah. Yeah, I love to know more about.
There's some more questions.
Right.
So I have a follow-up question on what we were talking about like generalized detail balance. So can I understand what you're saying by saying like those generalized detail balance apply to like non-equilibrium steady state as well?
Okay, so I'm not sure what you have in mind with the word generalized detail balance. So let me do this again. Where am I? I just lost all my screens. Hang on a second. So by generalized detail balance, do you mean this equation?
Yeah, like
Yeah,
you
so-
can have current, but they like kind of like the forward loop will have to like be like the strength of the forward loop will have to be equal to the backward loop.
Right. So if you have this condition for all loops in your rates, then you have detail balance. We used, I mean, I didn't know what you meant by the word generalized. If you mean that it doesn't depend on the existence of a Hamiltonian, then this makes sure that you would go to a state which have no currents, no probability currents. Okay, and
Right.
that is in the same class as the equilibrium state mech you learn in you know, with Boltzmann and so on. But if this is broken anywhere for any loop, then you would go into a non-equilibrium steady state with currents somewhere. It cannot all vanish, and there would be at least one current loop, if not more. And then the question is, what would that steady state look like? And that we don't know in general.
So what you're saying is like you always have like detail balance in like equilibrium system, but it doesn't matter or not. It doesn't matter if you have like Hamiltonian defined for the system or not.
Correct. So
Okay.
so Hamiltonian is just for systems where you define where you knew ahead of time what is an energy functional. But if you just define rates alone, okay, how does the stock change from one day to the next? Or how does the fire spread from one tree to the next and so on? To talk about forest fires or epidemics or whatever you want. You have those things and you don't have a Hamiltonian. You just have these W's. If you can somehow show that when your model is defined, that this is satisfied in all cases, then you can get to it, the answer of what the steady states are very, very easily. And then from those steady states, which means P star, right? Nothing stops you from taking the logarithm of it and calling it the Hamiltonian.
Mm,
Does that make sense?
right.
When
it
you
makes
get
sense.
there, you can call it the Hamiltonian. But non-equilibrium steady state, you can also call the P star, you know, log of P star Hamiltonian. But what you're missing in that case is the fact that there are non-zero currents.
Mm. I
By
see.
the way, on those of you who are interested in doing calculations just for the fun of it, and you know, I hate to keep using the word fun, but you learn a lot by playing in sandboxes. You know, we don't let kids play in sandboxes anymore, but we really should. And I think that's why I like Sid's talk so much. It just reminds me of being able to play. So you take ordinary random walk on a square lattice, right? 1/4 going to the right, 1/4 going to the left, and so on, and put it in a box, you know, with either periodic or brick wall conditions, whatever you want. You can solve it exactly, and everything is fine. But if you just take one link, any link you want, and make the hop from here to here, not with the probability 1/4, but with something smaller, let's say 1/10. Okay, just one link in the whole system. Make one link slower. Okay, and suddenly the system goes into non-equilibrium steady state, because in particular, the loop that going this way is different from the loop going that way, in the sense that only this link is 1/10. That one is still 1/4. This is 1/4, that's 1/4, this is 1/4, it's 1/4, this is 1/4. So going around this way is 1/10, 1/4, 1/4, 1/4. Going around this way is 1/4, 1/4, 1/4, 1/4. So in other words, this is not balanced anymore locally. All right. If you do that, you can still solve the problem exactly. And you would find the system has currents. in this case, even not just probability currents, but also the physical current. So you can imagine what happens, right? The particle goes out here and diffuses, and then when it comes to here, it's stuck a little bit. But when it comes over here, it can go across. So it likes to go this way, doesn't like to go that way. So there's a little drive. There's a little engine that drives it this way. And you have a dipole pattern all over the system. And as you know, dipole patterns satisfy the diffusion equation, except at one point, except at one link. And that's a very nice exercise. And you get to see that what happens here is that one loop doesn't satisfy the condition. The one above it also doesn't satisfy the condition. And then any loop that includes this link doesn't satisfy this condition. So there are lots of loops that doesn't satisfy this condition. Okay.
Can I ask another question?
Mhm.
So like for systems that's like non-equilibrium, usually cannot define a Hamiltonian for it, but there's like a field that's like has like a non-Hermitian Hamiltonian, which like satisfy PT symmetry that allows you to have like absorbable out of the system, absorbable like quantity out of the system. And with like non-Hermitian Hamiltonian, you can use the formal like method you use to treat any like equilibrium systems. Could you like comment on that? Is like that system satisfy detail balance because like it's dissipating? In principle, it shouldn't, right?
I'm a little bit lost. I'm not sure what you're asking. Instead of taking up time with the whole group, it sounds like it's quite detailed. Maybe you and I can Zoom one day. You can send me an email. I'm sure the email address is on the website, right?
Yeah.
Anyway, you look up my name and you can find my email address.
Okay.
What is your name?
Xuing.
Shing. Okay. All right. So send me an email and we'll set up a time and then we can just do a private chat.
Thank you very much.
Seems like something that I need to understand what you're asking. And it's a bit more complicated than, I think we have 3 minutes left, right, Leo?
Yeah. We're not very impromptu. Interesting question. We can go a little long.
Any more questions or comments?
In terms of going back to careers, I have a sort of a unique point of view. So I thought I'd just sort of advertise this. There are a number of rather famous universities that have satellite dark campuses that are often as big or bigger than the universities themselves. You know, MIT has the Lincoln Labs. Johns Hopkins has the Applied Physics Labs. Often they're at least 10 miles away. University of Texas at Austin has an Applied Physics Lab. University of Washington has an Applied Physics Lab. These are all basically defense-funded labs. But the Defense Department is extremely cognizant of climate problems and things like that. They view it as a worldwide national security threat. And they have a lot of money and they pay people very, very well. So these are places that should be of interest to you. So you can look up there. These, you know, in addition to sort of the standard government labs, you probably heard of DOE labs, NIST, NASA, you know, the JPL is part of NASA, NCAR, NOAA, and so on. There are all these much more sort of security and defense related sort of labs that still do incredibly good research work. Lincoln Labs, for example, is a center for quantum computation for whatever reason. You know, I guess, you know, from the defense point of view, they're interested in, you know, code, you know, breaking codes and things like that, obviously. So I just thought I'd throw that out as someplace you might consider in terms of career. They pay well. The projects are very exciting. They're much more goal driven than your standard NSF grant, right? And so there's like month by month, maybe every quarter or so, you have to follow up with your program manager to make sure you're making progress. That can sound onerous, but I find it very often you've got good people working with you on these projects, and generally you do. There's very, very, very good people. It's really exciting. It pushes things along in a very, very nice way. They worry about space weather, solar activity, things like that. Very fundamental physics, which affects satellite communications, guidance systems, you name it. So there's a lot of really, really good research related to these things. And so I just thought I'd call that out.
Okay, well, I think it's probably time to bring things to a close. I want to say how much I enjoyed being here these past 4 weeks, even though I got COVID in the middle, and how much I learned. It felt like drinking from a fire hose at times, but I really enjoyed getting to know some of you, and I look forward to seeing you out there in the future.
Any final farewells from our boss?
I'll just repeat, echo what Brad said. So thank you all for coming. I hope you enjoyed the physics, learned a lot, but also enjoyed, meeting each other and Boulder, town of Boulder, but also the surrounding. Hope you took advantage of it and spread the word about. She enjoyed the school. Spread the word, so we have continue having, phenomenal students apply each year. And the other thing I'll urge you is stay together. Stay in contact, and many of you will continue in academia, and keeping those ties going. Next March meeting or whatever other common meeting, organize dinners and get-togethers. That's a very physics is a very social activity. So it's wonderful to see, you guys will enjoy seeing each other in a year or two or many years forward. And then as you continue your careers and undoubtedly move on to faculty positions, don't hesitate to then, send your own students to our school and also put in proposals to organize schools, future schools, Boulder summer schools. And I guess the final thing I will say is don't forget to please fill out the electronic feedback. We try to improve the school and that's all based on your feedback, positive or negative. We like hearing positive things, but we also like constructive criticism that we use to then to benefit future students. Okay, thank you.